Have you ever wondered how massive data centers, we're talking the ones that power our entire digital world, keep up with that relentless, nonstop flow of information? Well, the secret, a lot of the time, is in a really elegant design called the Layer 2 Leaf and Spine Network. And today, we're going to break down exactly what that is and why it's so incredibly important. All right, here's the game plan. First, we'll look at the massive traffic jams that used to plague older networks. Then, we'll introduce the hero of our story, the Leaf and Spine solution. We're also going to uncover the key piece of tech, MLAG, that makes the magic happen, touch on some really critical design choices you have to make, and finally, wrap it all up with the real-world payoff of this awesome architecture. So, let's set the stage. Why was a whole new network design even necessary in the first place? Well, it all comes down to a fundamental change in how data moves not into the data center, but inside it. Think about it this way. Back in the day, most network traffic was what we call north-south. That's data flowing from you, the user, into the data center, hitting a server, and then coming back out. But today, that's just a tiny fraction of the picture. The real action is inside the data center, and that has completely changed the game. See, legacy networks use this pretty rigid three-tier model. You had your access, your aggregation, and your core layers. And look, it was fine for that old north-south traffic pattern. But you can see it's kind of clunky, right? It introduces extra steps in complexity compared to the super streamlined two-tier leaf and spine model that's really become the standard today. And this is the absolute key. Modern applications create a ton of east-west traffic. This is where servers are constantly talking to each other all day long within the data center. The old three-tier design just wasn't built for this kind of internal chatter, and it created these massive, massive traffic jams right at that middle aggregation layer. And here's the main villain of the story, a protocol called Spanning Tree, or STP. Its main job was to prevent network loops by, well, simply blocking any redundant paths. Now, this meant you could have perfectly good, expensive, high-speed connections just sitting there, totally idle, completely disabled by the protocol. Imagine paying for a 4-lane highway, but only being allowed to use 2 of the lanes. It was just incredibly inefficient. And what's worse, recovering from a failure was painfully slow. So how do we solve this data center traffic jam? How do we finally unlock all of that bandwidth we paid for? Well, let's introduce the solution, the elegant and super efficient leaf and spine topology. The concept behind this is actually beautiful in its simplicity. Instead of 3 tiers, you only have 2. You have your leaf switches, that's where all your servers plug in, and then you have your spine switches that form this high-speed backbone. And here's the golden rule. It's this simple. Every single leaf connects to every single spine. Just by ripping out that middle aggregation layer, the whole network becomes much flatter and way more direct. What this means is that data traveling between any 2 servers now only has to make, at most, 2 hops. It goes from the starting leaf up to a spine and back down to the destination leaf. That's it. This consistency makes network delay or latency both incredibly low and super predictable. The core principles are really what make this design so powerful. Okay, so we know every leaf connects to every spine. But just as important is what doesn't connect. Leaf switches never ever connect directly to other leaf switches, and spine switches never connect to other spines. This strict grid is what creates this beautiful web of multiple, active, and equally fast paths for data to travel on. But wait a second, if we've got all these connections and all these paths, what stops us from creating the very same network loops that Spanning Tree was supposed to prevent in the first place? It's a great question, and this is where the real magic comes in. The key is a technology called multi-chassis link aggregation, or MLAG. It's a really clever protocol that lets 2 separate physical switches, like 2 of our spine switches, basically work together and appear as one single logical switch to any device that's connecting to it. And this, right here, is the absolute game changer. Because that leaf switch now thinks it's connected to just one big spine switch, it can use all of its physical links at the exact same time. We call this an active-active state. And with no risk of creating network loops, there's no need for Spanning Tree to come in and shut down our valuable connections. The blocked links are gone. So the bottom line is that MLA gives us the best of both worlds. We finally get to use 100% of our network bandwidth. We get true built-in redundancy, because if one of those spine switches fails, the traffic just keeps on flowing through its partner without missing a beat. And that network recovery time, it becomes lightning fast. And this whole concept even extends to how servers talk to the rest of the world. MLAG works hand in hand with protocols like VARP, or Virtual ARP. This allows two-leaf switches to share a single gateway IP address, creating a fully redundant active-active path for servers to send traffic off their local network. Okay, so the theory is solid. It makes a ton of sense. But how do you actually design one of these networks in the real world to guarantee you get the performance that your applications desperately need? Well, one of the most important things to think about is a metric called the subscription ratio. Now, don't let the name intimidate you. It's really just asking a simple question. How much more traffic could my servers possibly send than my uplink paths can actually handle? You're just comparing the total bandwidth of all the servers connected to a leaf switch against the total bandwidth going from that leaf up to the spine. And in this game, a lower ratio is always better. A perfect 1-to-1 ratio, that's the dream. That gives you what's called a non-blocking network, where, in theory, every server could transmit at full speed at the same time without ever hitting a bottleneck. But a more common 3-to-1 ratio is often the sweet spot for general computing, and it means you have 3 times as much potential server traffic as you do uplink capacity. And this is where you get to tailor the design for your specific needs. If you're running high-speed storage that absolutely cannot tolerate any delay or packet loss, you engineer for that perfect 1-to-1 ratio. For general-purpose servers, a 3-to-1 ratio usually hits that perfect balance of cost and performance. And for some less demanding services, you can even push that ratio a bit further. It's all about engineering the network for the job it actually needs to do. So let's bring it all together. After you've put in the work, you've implemented with new technology in this design, what's the ultimate payoff? What kind of data center network have we actually built? What we've built is a network that truly meets modern demands. We've got redundancy through MLAG? Check. We've got seamless scalability by just adding more spines or leaves? Check. We can have a non-blocking design and avoid congestion? You bet. And because it's all built on open, standard protocols, we're not locked into one single vendor. It ticks all the boxes. The end result is a network foundation that's incredibly resilient, delivers predictable, high performance, and can easily scale out to meet whatever demands the future throws at it. This is exactly the kind of modern network foundation you need to run today's complex, data-hungry applications. This quote really sums it up perfectly. It highlights that we're still using standard, familiar Ethernet technology, nothing crazy or proprietary, but we're just combining it with modern design principles to build something that's way more powerful and resilient than anything that came before. So the Layer 2 leaf and spine architecture really does an amazing job of solving that critical east-west traffic problem that crippled older designs. And that leaves us with a final question to think about. Now that we've cleared this major choke point, what's the next bottleneck your network needs to solve?